Bismillah ar-Rahman rahim. So, in this lecture, I'm going to explain how to calculate the interplanar separation, and this is the by using the Miller indices and what would be the equation and what is the way to calculate the diffraction angle, and this is the theta HKL, and also you can calculate the diffraction planes or the Miller indices. And this is very important calculation. By using the XRD data, you can calculate the HKL values. And here I'm going to give you the brief explanation, and later on we will do one exercise how to calculate the Miller indices. So first of all, the separation between two successive lattice planes of the cubic, tetragonal, and the orthorhombic system. Uh, in these systems, edges are mutually perpendicular. That means the angles between the alpha, beta, and the gamma is 90 degree. That's why these are perpendicular to each other. And this particular equation for these three systems, and you can solve the three-dimensional form of the Pythagorean theorem, and that will give you the following expression. And for the interplanar distance for the cubic system, where the three length of the intercepts are equal to each other, a equal to b and b equal to c, and you can just put the value of a instead of b and c, and when you take the LCM, that would be the a square. So the and again this equation will become this, and when you uh, inverse this equation and removing the square of this one, of course you must have to take the under root. When you take the under root and this a square under root cancel out, this will become a, and this would be the under root h square plus k square plus l square, and this is also the reverse of this equation or the inverse of this equation. And in this ABC actually are the intercepts along the XYZ axis, and HKL are the Miller indices. Again, I have explained in detail the ABC and the HKL values, how to calculate the Miller indices in one of the previous videos. But here we indirectly we will calculate the Miller indices by using the equations. And here is the uh, equation, the first for the calculation of the diffraction angle, and that is called the theta HKL. And these are the actually the two equations we are going to use to calculate the interplanar separation. And this is the d spacing for the to be used for the Bragg's equation to calculate the interplanar distance. And this we have already explained. And this is another equation which is given over here. This is the interplanar separation. To calculate the interplanar separation by using the HKL values, that is the Miller indices. So there are two ways to calculate the interplanar separation: by using the Bragg equation, and by using this equation by that means by putting the value of the HKL. So these two equations are equal to each other. Let's suppose by comparing the both equations, and you can get the value of the sine theta over here. Just this is the rearrangement you can take over here, and then it will be the dividing this whole equation with n lambda over 2. This will become reverse. So sine theta will be equal to this, and again sine theta HKL, that again just rearranging this equation L lambda over 2a, and this will be the HKL under root. And when you take the square of this one, this would become the square, square, and square. This is going to cancel out, and this would left. And again sine theta square, that means it is you have to write in this form sine square theta, not sine theta square, because here sine actually this would be the equal to the sine theta HKL multiplied by sine theta HKL. This is the sine square theta. So there is actually with the calculation there is no change in the final value, but this is the right way to express this in this form, and this is the sine square theta equal to this whole value. So you can calculate the sine theta or the theta, uh, and you can also calculate the sine square theta by using this equation and sine theta by using this equation, and somehow these two are important to be used for some sort of the calculation. So here it is the equation to use to calculate the Miller indices, and these are the HKL values. So again, this is the equation we have actually derived before, and when you have to calculate the HKL values, so you can get by just rearranging this equation. So h square k square plus l square will be equal to this. And this you have to multiply, and this will be the going to divide. And these all are the square value. That's why I have taken the square of the whole parameters. So by using this equation, you can also calculate the HKL values. And here, this intercept is required, and this is the sine, this is the theta, diffraction angle, and is the any number 1, 2, 3. What is the order, as explained in the Bragg equation, and lambda is the wavelength of the source of the X-ray. So let's start with an example. X-ray diffraction of copper, which has a face center cubic structure, and the lambda value is 0.154 nanometer, and one peak of the X-ray pattern, let's suppose at 2 theta is 43.2 degree for the first order refraction, and you have to calculate what are the Miller indices. So the first is to calculate the A, and here theta is given, lambda is given, n is given, that is the first order, and A is unknown. And for the phase center uh, cubic structure, the A will be equal to 2r under root 2, and r is the atomic radius having the value of 0.128 nanometer. And when you put the value of this in this equation, so this is the answer of this one, 0.362. Now you can use this equation as we have derived before, and you just put the values of all these over here. And other important thing is this is the value of 2 theta, 43.2 degree, and here the theta is given, so that's why you have to divide by 2 to get the value of the theta, because in data there is 2 theta is given. So theta is 21.6, 21.6, and when you put all these value, n is 1 and lambda is 0.154, and the value is 1.73. When you take the square of this one, that would be 2.99, that is equal to 3. So h square plus k square plus l square will be equal to 3, and this is given over here. And when the value is 3, this is the only plane which you can get when the value of HKL is 3. How? Just put the value of 1 for H, K for L, and 1 for sorry, 1 for K, 1 for L. When you solve this one, this is the value of 3. So the plane is called the 111. So this is the way you of with the final values, you can suggest what is the HKL plane, because this is the whole number which you the data will give you the value of this, and by using this value you can explain what would be the possible plane. And here you can say this is the HKL plane is 111. So this is the way how can you calculate the Miller indices HKL value with the theta, that is the diffraction angle, is given. So here is the sum of the planes are given over here. So we have discussed the example of if your sum of the square of the HKL value is 3, then your HKL plane is the triple one. In a similar way, if you will get the value of 1, then this would be the possible plane 1 0 0, or you may say 0 1 0, or it may be 0 0 1. So in all these planes you will get the value of 1. So if your value is 2, this is the possible plane, because here 1 square plus 1 square plus 0, that will give you the final answer of 2. Let's suppose this is the plane 6, and again how can you get the value of 6, and this is the possible plane. So that means when this is the HKL 2 square plus 1 square plus 1 square, so 2 square is equal to 4 plus 1 that is the 5, as 5, and plus 1 is 6. So 6 value will give you this plane. So this is the actually the final uh, version of this explanation. If you will get the sum of all these square equal to any one of these value, then your plane is written over here, and these are called the HKL planes. So remember, there is no value of the 7, because you will not get the 7 when you put the values over here. So it is not possible to get the value of the 7. So you cannot have the plane that is the sum of all these square will be equal to 7. So no plane of HKL exists which is having the value of 7. And of course you can use these equation to calculate the HKL values. This is the last slide, and this is about the X-ray refraction data of NaCl. Theta is given, and again this is the equation. This is the modified form of this equation, because 2a and lambda is the constant, only sine square uh, theta is the changeable, and this is given over here. So this maybe you can take as a common and calculate the value is 0.188 in case of the NaCl. So when you just put the values of theta over here, you will get the value of 3, 4, 8, 11, 12, 16, so on. And these are the actually the values of the h square plus k square plus l square that is given over here. So when you put the value, get the value of 3, that means the possible plane would be the 111. If it is 8, then the possible plane would be the 2 to 2, because 2 square plus 2 square, that is equal to 8, and the value is 8. Let's suppose this one, and the plane is the 311. 3 square is the 9 plus 1 plus 1, that is 9, 10, and 11. 11 is the answer of this, or the value of this one, and the plane is called the 311. So in a similar way, you can get the plane if you know the value of the theta, and just put the value of the theta over here, diffraction angle, and you will get the Miller indices. So this is all about our total lecture.